Okay, so in the last class we talked about the application of dimensions. What were the main application of using dimensions? One, we can check the correctness of equation. To check correctness of equation. The other was to derive an equation. To derive an equation, but there was certain limitation that we can derive only the equations which are based on not more than three quantities. And while deriving the equation, there was one more limitation that we get a constant whose value remains undetermined using the concept of dimension. Also, we use dimension to convert from one system to another system. So we will do mainly the problems today based on dimensional analysis. We call this as dimensional analysis. Okay, the first question, let us see the time period T of a pendulum depends on the length of the pendulum and the acceleration due to gravity. Acceleration due to gravity. Now we have to find out the expression of time period of pendulum using dimensional analysis. So here we have the time period with us. That means its unit is second. It depends on the length of the pendulum. Let us say L is the length of the pendulum and acceleration due to gravity. So T directly proportional to length, let's say to the power x, T directly proportional to acceleration due to gravity, let's say power y. Now combining this, we get T is equal to K L raised to x G raised to y. So we will just equate the dimension on both sides. So for time it is only T and L is the length. Acceleration due to gravity, what is the dimension? Lt to power minus 2 and raised to y. So we will just compare the dimensions on both sides. So L to the power x here, and this becomes L raised to y. So L raised to x plus y times T raised to minus 2y. So from here we get two equations. One, x plus y is equal to 0, right? Because on the left hand side there is no length, that means L raised to 0. So x plus y is 0 and minus 2y is equal to 1. And this gives us y is equal to minus 1 by 2. So if we put this y here, we will get x as 1 by 2. That means we get the equation now. What is that equation? T is equal to K L raised to 1 by 2 and then G raised to minus 1 by 2. So that means T is equal to K L by G root over. So this is the time period of the pendulum, provided that here we do not know the constant. That's all we can do using dimension. But really, if you see the formula of time period of pendulum, it is 2 pi root L by G. So this 2 pi, how did we get? This is using the experiment. We could have followed some experiment and we would have got exact value of the constant. But this is what we can get using dimension. Okay. Okay, let's say we have another question and P plus A by V square times V minus B is equal to CT, right? This is the equation, and here we have, I'll give the meaning. P is the pressure, P is the pressure here, V is the volume, and T is the temperature. A, B, C are constant, as you can see in this expression. A, B and C are constants. You have to work out the dimensions of, as well as find out the units. Dimensions, units we have to find of A, B and C. So you can just pause the video and you can start doing this one. So here we have this equation, and what we will do, their dimensions must be equal on both sides. So you can say this dimension is pressure, so this dimension will also be equal to the dimension of pressure, because according to principle of homogeneity, only the quantities with same dimensions can be added or subtracted. So the dimension of A will be P times V square. So for pressure, what is the dimension? It is force per unit area. And for V square, what is the dimension? It is L square. So for L cube, for area it is L square. So this dimension of A is nothing but dimension of force into L. That means ML. Okay, this is V cube, V square, right? So V square means we square it here. So let us square that and then put here. So V square, the dimension is L raised to 3 and square of this divided by L square. Yes, and that is F L to power 6 by L square. That is, for force it is ml t to power minus 2 times L raised to 4. So yes, for A I have got ml to power 5 t to power minus 2, the dimension. Talking about the dimension of B, here we can see the term V minus B. That means for B the dimension will be same as the dimension of V. So that will be L raised to 3. And talking about C, what should be the dimension of C? The dimension on the left hand side, if we observe, this dimension is the dimension of volume. Both their dimensions are the dimension of volume. So for volume, whatever dimension we will have, we will multiply that with the dimension of pressure, and then we will divide that by the temperature. For temperature, we have the representing unit K. So that will be dimension of C. So for pressure, it will be force per unit area. That means ml t to power minus 2 divided by L square times, for volume we have L cube divided by K, and that will be m L square t raised to minus 2 K raised to minus 1. Yes, we get the dimension of C, B and A. So dependent. So here we have the next question. It is also dependent on how we derive an equation. So this is the application of dimensional analysis. We'll do one more problem. So let us say that we have given that the velocity of a wave is dependent on let's say the tension. So I'll give the meaning here. Tension is a kind of force, we have already seen. So tension in the string represented by T, and mass per unit length of the string, and this is represented by mu. Now we are supposed to find the expression for velocity of a wave so you can again try doing this problem. Yes, so directly what we do, we'll just use the direct expression, velocity dependent on tension. So V is equal to K T to power A and mass per unit length raised to power B. So velocity, the dimension is LT to power minus 1 is equal to K. Dimension of tension, it is ML T to power minus 2 raised to A. Dimension of mu, that is given here as mass per unit length. That means ML raised to minus 1 to the power B. So let us compare the dimension on both the sides. We get M raised to A plus B, right? We will just simplify both of them. L raised to A minus B, T raised to minus 2A. So we will just compare any two equations we want. So let us take this minus 2a is equal to minus 1. So a is 1 by 2. Similarly, let's take this one. So a plus b is 0. So b is minus 1 by 2. So we get v is equal to k times t raised to 1 by 2 mu raised to minus 1 by 2. That gives v as k root t by mu. This is the expression of velocity of the wave which we have found, and by experiment k value comes out to be 1 in this case. So later on in oscillation chapter, oscillation and waves, we will use this expression of velocity, that is root t by mu. Some other things we will do apart from dimensions which we have left, that is the fundamental units. If we consider, let us say I consider the mass. I am talking about the basic fundamental units. These are also only basic units, but I am talking about the most common one. So mass, length and time. Amongst this, if I talk about mass, now it depends upon what kind of mass we select. If the mass is very big, then we have to find its mass just by experiment. So like if I tell the example, let's say I want to find the mass of Earth. So definitely I'll have to go through certain calculations or certain other hypothesis to get its mass. Of course, I cannot measure it because it is so huge. But if we talk about, let's say, a ball, I can measure its mass. I can put it over the instrument and I can read its value. If we talk about, let us say, proton or an electron, now its mass is measured by a very fine microscopic instrument. So there are different scales for the measurement of mass, we can see, depending on the size, depending on the quantity. And the same manner, talking about the length, it depends what length we are going to measure. So for example, if you see the dimension of atomic size, so atomic size is nearly up to 10 raised to minus 10 meter. In terms of 10 raised to minus 10 meter, if you see nuclear size, it is 10 raised to minus 15 meters. It's of this size. If we talk about the distance from Earth to Sun, that distance from Earth to Sun, if we talk about this distance is very huge number. So of course we cannot set a standardized instrument or take a ruler and keep measuring all kinds of lengths. So there are different scales for this measurement, and we will talk about in what manner the distance from Earth to Sun is measured, right? These are the three important things. So not only we will see the Earth to Sun distance, but we will also see the distance between any two celestial bodies in the universe, how they are measured. So we have three units of measurement. One, astronomical unit. Another one is light year. And third one is parsec. We call it as parallactic second. So looking at the definition part, astronomical unit, it is the distance from Earth to Sun. Now we have set that one astronomical unit will be the distance from Earth to Sun. So if I want to get the distance between, let us say, Jupiter to Sun, then this distance might be in terms of hundreds of astronomical units. So for example, let's say it is 100 astronomical unit. That means we must have certain value for astronomical unit. So how do we calculate this value? So generally we know that light takes 8 minutes 20 seconds approximately to come from Sun to Earth. So if we are talking about light, that means it will have its speed. We are talking about the speed in the space. So 3 into 10 to power 8 meter per second. So convert this in seconds and we have this speed. We'll multiply that and we will get the distance. And that distance is itself what we call it as one astronomical unit. So you can calculate the distance. Let us see what this calculation gives us the result as. So after the calculation, we get the value for one astronomical unit, that is 1.496 times 10 raised to 11 meters, or you can remember it approximately as 1.5 times 10 raised to 11 meters. So this was about astronomical unit. Talking about light year, what is light year? It is the distance. So if we see the dimension of light year, we must remember it is a distance. So its dimension is L. So distance from, or distance traveled by light in 1 year. So if we want to calculate the value of 1 light year, that will be distance traveled by light in 1 year. So we are talking again about the light. So 3 into 10 to power 8 into 1 year. 1 year I should convert in seconds. So 365 times 60 times 60 times 24, and using this calculation we will get the value of light year. So that comes out to be 9.46 times 10 raised to 15 meters. We have the expression of parsec as well. We will see what is 1 parsec or 1 parallactic second. So this is definitely used to measure the distance, you can say large distance of astronomical objects. So it is used to measure, we can say, astronomical distances. And how do we define a parsec? What it is actually? It is the distance from sun to an astronomical object, from sun to an astronomical object that has parallax angle. I will tell what is parallax angle. So it has parallax angle of 1 arc second. So what is parallax angle? Let us understand. So let's say we have a distant star. Let's say this is a star, and this is, let's say, sun, and this is earth, which is revolving around the sun. So let's say this is a star, and we want to find the dimension, the angle subtended on the star. So whatever angle will be subtended on the star from two distant locations of earth. So here these are the two distant locations of earth. This angle is 1 parsec. We call that as 1 parallactic second. Right? This is 1 parallactic second. So it is very clear that this distance is 1 astronomical unit, and this angle we call it as parallax angle. So how do we find out this theta equal to L by R? We have learned this in trigonometry. So this is angle theta is equal to L. L comes here, it becomes the diameter of this earth. So I'll write this as D divided by R. R is 1 astronomical unit. So what angle is subtended on the star, using that we can get the distance. Or if we know the distance, because this is very much true, it's even possible, if we know the distance, that means the diameter, then it's possible to calculate even what angle is subtended here. So 1 astronomical unit, you can see I have taken, that means I am sure that this star is at the same distance as the sun is from earth, right? This distance is also 1 astronomical unit. So we have gone through the basics of units and measurement, what is required in order to complete the numericals. So you can practice the problems and we can meet in the next class. So overall we should get a value of parsec here. So generally if this theta is 1 second and the distance is 1 astronomical unit, then in this case we can get the dimension. So we can define 1 parsec as the distance at which an arc of length 1 astronomical unit subtends an angle of 1 second. So that means let us understand this with respect to the diagram. Okay, this is just a trigonometric relation how we will use. But what is 1 parsec? Okay, this is the distance at which an arc. So what arc? So Earth is revolving around the sun. Let us see here like this. So if we talk about this length, it is 1 astronomical unit. So let's say this is the star whose distance I want to measure. So 1 astronomical unit, if it makes 1 second angle here, right, then it is possible to find out this distance. So again what we can do, we can just use theta equals to L by R. So this becomes L and this becomes R. So exactly similar knowledge we are using, whatever we have used here at all the places, but here instead we have a fixed value for parsec, that this distance will be in parsec, or we will call that as 1 parsec. So we have a value for 1 parsec when this arc length is 1 astronomical unit and the angle subtended is 1 second. So if you are talking about 1 second, you should consider this in SI unit, because I have given you the conversion. Pi radian is 180, 1 degree is 60 minutes and 1 minute is 60 seconds. So 1 parsec is numerically equal to 3.08 into 10 raised to 16 meters. So you can take them down, and then finally we will see the relation between the three lengths, the three units which we have seen. So between the parsec, between the astronomical unit and between light years. So let me write here the relation between astronomical units. So 1 light year divided by 1 astronomical unit, then you will get the result, the relationship between them. So you can just divide them because we have the value of 1 light year. So if I just put the value, for instance, 10 raised to 15 divided by 1.5 into 10 raised to 11. So we will get that as 6.3 into 10 raised to 4. So what can we conclude by this ratio? That 1 light year is 6.3 times 10 raised to 4 astronomical unit. So similarly, you can find the relationship between other units what we have gone through. So the rest we will cover in the next class.